Good afternoon, everyone, and welcome back to the first presentation of the Metro Atlanta chapter of the AMS and NWA's Fall Webinar Series. My name is Sid King, and I'm the current president of our local chapter for the year of 2020. This summer, we launched our first ever series to encourage the sharing of scientific knowledge and to create educational resources that are free for everyone to use, even in spite of our chapter not being able to meet up in person due to COVID-19 concerns. And we're excited to do it again this fall, following the same principles. We've had 5 presentations of our first series this summer, and we're slated to have 6 more presentations coming up this fall. Our lineup this fall, as you can see, is still taking shape. But we will continue to keep you all updated with the latest info on presentation topics as those get finalized. For anyone that would like to see the previous webinars you may have missed or would be interested in learning more about, the presentations have been uploaded to the Metro Atlanta AMS NWA YouTube channel. It's my privilege today to introduce today's speaker, Dr. Victor Gensini. Victor is an associate professor in the Department of Geographic and Atmospheric Sciences at the University of Northern Illinois. Today, he'll be giving a presentation on the topic of his specialty, subseasonal severe weather forecasts. If you have any questions about this topic, feel free to type them into the chat window and we'll answer them at the conclusion of this talk. Are you ready for me to hand it over to you, Victor?
Yep, I'm ready whenever you are, Sid.
Thank you.
All right. Well, thank you for the introduction. It's unfortunate that I can't be there in person to give this presentation, but there are, I guess, some good things that come out of COVID, and one of them is forcing many of us to get more comfortable with online meetings. And so, as Sid mentioned, I'll be talking a little bit tonight about extended range severe weather prediction. I do have a lot to cover, and so I want to dive right in here with some of the latest and greatest on the cutting edge of predicting out really beyond what's capable with numerical weather prediction, as I'll show here in my introductory slides. So just really quickly and briefly about me, I like to do this at the beginning of my talks, is just sort of give you a collage of who I am. I'm obviously a scientist, but there's a lot more to scientists than just sitting in our labs and sitting behind computer terminals and crunching numbers and doing research. I do get out in the field every year and really like to take in situ measurements and get close to severe convective storms. It certainly has helped me become a better forecaster and experiencing them and getting close to them. And just some of the other things, if you've ever used the College of DuPage weather forecasting website, I had a large hand in the development and change of those forecast graphics, as well as the satellite pages when I was an instructor at College of DuPage before moving to NIU, my undergrad institution. And I actually also spent some time in Georgia. I got my PhD from the University of Georgia there in Athens, and so I actually have attended meetings of the Atlanta Metro AMS chapter in person. This was back when I think Daniel Dix was the president at that time. So I do have roots back in Georgia as well. Like many of you probably listening to this call, I'm a giant costume, my Halloween costume, which I will break out here in a couple of weeks for Halloween. I'm always the extratropical cyclone and like to really instill passion of weather and forecasting into my students. I got interested in atmospheric science after the Granville, Utica tornado of April 20th, 2004 that started in north central Illinois and tracked across the Illinois River and unfortunately killed and injured 8 people in the town of Utica. That particular forecast wasn't a particularly well a good forecast from the Storm Prediction Center. The morning risk was a marginal risk, and things quickly evolved throughout the day. This was along a rapidly northward retreating warm front, and folks recognized this particular event, and watches and warnings ensued. Perhaps a little bit closer to recent, one of the things that stems a lot of my research is the big severe weather season in the southeastern United States of April of 2011. And what you're seeing here are the inlets here. In the inset picture is all the tornado LSRs from April 1st to April 30th, 2011. And in the bottom right, the color fill is the number of hours from the North America Regional Reanalysis, the NAR, that the significant tornado parameter was greater than 1. And so just kind of qualitatively, like looking at these two maps, right, you see a lot of qualitative correlation between environments that were very favorable for tornadoes and where the tornadoes actually occurred. And we've presented a paper or submitted a paper, and it's been published in the Journal of Applied Meteorology and Climatology through the AMS that sort of looks at these relationships between tornado environments and where tornado events occur. Well, of course, that is fine and dandy, and that actually launched the what stemmed into congressional appropriations for Vortex Southeast, which is a field project, as many of you are well aware, to study tornadic storms across the southeastern United States, not just physical aspects of them, but also societal vulnerability aspects. And then, of course, the first year of the field project, this is what happened, right? Very, very few LSRs, an overall environment throughout the month that really did not support tornadic activity. And so one major research question that I had coming out of 2011, 26, and seasons after, what creates in April 2011 versus in April 2016, right? They're both at the same point in the annual cycle. You know, ideally you'd think, well, what causes an active April versus a non-active April? And trying to look at some of the drivers in climate variability that might be at play. So one of the research questions that I've been asking recently are, you know, how do the leading modes of climate variability really impact severe convective storms? So tornadoes, damaging large hail, and damaging convective wind gusts. How skillful are we right now at actually doing this? So that requires a look at numerical weather prediction. And a question that I'm not going to address tonight, but I have looked at in the past, is how climate change may impact severe convective storms in the future. And if climate change is not already impacting severe convective storms, is there any sort of theoretical potential impact in the future? A lot of my research involves high performance computing, statistics, a lot of modeling, and most recently machine learning and artificial intelligence to try to sift through these vast amounts of data that we have, looking for signal in a lot of potential noise. That requires things like GIS and data visualization to help you do that. So the first research project that I'd like to present to you tonight actually stemmed out of a collaboration at the NOAA Hazardous Weather Testbed. And for those of you in the National Weather Service or who consider themselves operational forecasters, if you are interested in severe convective storms, I highly encourage you to spend a week at the Hazardous Weather Testbed to really saturate yourself in some of the latest and greatest tools and techniques that are being used to predict severe convective storms. My basic question that stemmed out of this collaboration was, how well does our flagship model in the United States, which in terms of extended lead time would be the GFS, predict severe weather? I mean, it's a very, very simple research question. And I think what falls out of that is, what forecast lead time does this skill that the GFS might have diminish to zero? So I've published this paper in the journal Geophysical Research Letters last year, and you can take a read of it if you're interested in more. I'm going to touch just very briefly on some of the results from the paper here. So the idea, as many of you are well aware, the Storm Prediction Center creates outlooks for severe convective storms. Right now, they do that as many as 8 days in advance in various capacities. Most of you are probably most familiar with the categorical outlook, which is basically just a scale of 1 through 5 of the threat level for severe weather on any given day. You can sort of think of it as the Homeland Security terror threat level. But instead of terrorism, it's for severe convective storms. So for the public, this is great. It gives a really simple kind of 1 through 5, what's the potential in your area for severe weather? As a scientist, we need to sort of quantify the level of risk, right? So the quantification here comes from probabilities. And what drives the categorical outlook are the probabilities for severe storms. So I show you this example here from April 9th, 2015. This was the Rochelle-Fairdale EF4 tornado across northern Illinois. The Storm Prediction Center had a 10% contour for probabilities across northern, central, and eastern and western Illinois. Now, what does this 10% actually mean? Okay, you can see they had a 10% for tornadoes, they had a 30% for hail. What does this actually mean? what actually means is the forecaster is drawing contours for probability based on the likelihood of something happening within 25 miles of a point. So for example, let's say on this particular day over DeKalb, a forecaster, this is DeKalb, Illinois, not DeKalb, Georgia, DeKalb County, Georgia. This is DeKalb, Illinois. Forecaster is going to say there's a 5% chance here of a tornado happening within 25 miles of a point. And then they would go to another spot in the grid and they would say, here, there's only a 2% chance. Here, there's a 2% chance within 25 miles of a point, and so on and so on. And then eventually what happened is the forecasters would essentially connect all those contours and the SPC probabilistic outlook would be made. In this particular case, a 2% contour for tornadoes and a 5% contour for tornadoes within 25 miles of a point. So what you're basically saying is anywhere inside of this polygon, there's a 5% chance of a tornado happening within 25 miles of a point. Doesn't seem like a high probability. However, we are talking about extremely rare events, tornadoes, where the 5% contour is actually significantly higher, right, than the background climatology of having a tornado. These probabilistic values are then converted to the categorical table. So for example, if you have a 10% tornado, I'll get my little, let me get my little annotation pen going here. If we have a, you can tell I'm a teacher, I have all these nasty or silly gadgets here. If we have a 10% tornado, that corresponds to an enhanced risk. If we have a 30% hail, that corresponds to an enhanced risk, and so on and so forth, okay? So we're gonna use this idea of forecasts that the SPC use to try to verify our forecasts, okay? So we're gonna sort of create a hindcast here, as you'll see in just a minute. Okay, so you make this forecast, okay, and then the events happen, which in this case are the red dots, so the tornadoes happen, and then you look at it and you go, well, I'm a forecaster, I need to verify my forecast. How do we grade? How do we give this forecast a grade? And the answer here is, it's not easy. Some of you would look at this forecast and go, that's a pretty good forecast. I would give it a B+ or an A-. What about all the false alarm area in Indiana and Ohio and Kentucky, right? And we did have 2 tornadoes down here in Eastern Texas, so you got to give them credit for the southern extent. How do you grade a forecast like this, right? Here's another example, right? 10%, we even have a 15% tornado contour here in this example from February 28th, 2017. How do you grade that? That's a pretty darn good forecast. There is some false alarm area. Okay, here's a high risk, 30% hatch tornado. A lot of the tornadoes happened outside of the 10% contour. How do you grade that? No tornadoes happen in the 2% contour. So we need a way to quantitatively judge or grade these forecasts that are happening from SPC. Here's another example, okay? So how do we do that? We use the practically perfect approach. And this has just been published in the bulletin of the AMS. So I think the next issue of BAMS that you get delivered to you, if you have access to BAMS, you'll see our paper about practically perfect and the climatology of practically perfect in BAMS. The idea is basically here, we have a set of LSRs, we assign them to a grid, and we perform a Gaussian kernel smoother over the grid that would represent the uncertainty associated with forecasting this particular event. So at the end of the day, what we're basically doing is trying to reconstruct a perfect SPC forecast knowing what happened, okay? So it might look something like this. This might be what an example of a perfect SPC forecast given this set of tornado LSRs. So for the example that I showed earlier, let's take a look at this. Okay, here's the forecast from SPC. We have a 10 hatched, and here's the actual practically perfect probabilities from that same event. Okay, so now that we have the target, this is essentially going to be our target. We're going to try to forecast the practically perfect grid. We need a predictor. So the predict and our target is going to be the practically perfect grid, and our predictor is going to come from the GFS. So I want to talk about that next. So let's take this sentence and break it apart. How well can the US flagship model predict severe weather? How well can is going to be addressed by skill statistics, things like probability of detection, false alarm ratio, critical success index, and so on. The US flagship weather model is going to be the GFS ensemble. We're going to use all 20 perturbations and the control member. That will be our predictor. And then severe weather, our target will be the practically perfect fields for tornado and hail. We're going to be specifically predicting the slight risk thresholds for both tornado and hail. So for tornado, that's 5%, and for hail is 15%. Just a little bit about the GEFS. If you're not familiar, it actually has just undergone an operational change, and I'm really excited about the new version of GEFS. I've already downloaded over 25 terabytes of data from the new GEFS. It does go out to 35 days every Wednesday, and there are an increased amount of members, and so maybe we can talk about that later. But this study was done with the previous version of GEFS, which again has 21 total members and 6 hourly output out to 16 days. It does have global coverage, although this study will only look at over the United States. We're going to use environments as a predictor, which is similar to the outlook process. We don't forecast in the outlook process where specific tornadoes are going to be. Rather, at that time frame, we're looking at general spatial areas where we expect tornadoes to be occurring. The specific predictor that we're going to be looking at from GFS is the supercell composite parameter, which is listed here. And you can see more information about the SCP in Thompson et al. 2003, essentially combining instability, low-level storm relative helicity, and deep layer vertical shear. We're also masking the SCP if it doesn't have precipitation in the following time step, meaning that either convection did not develop in that environment, it could have been too capped, there wasn't a lot of forcing, whatever it might be. But we only want to look at predictions from the model where this environment was occurring and actually the model did produce convective precipitation. So if you've ever looked at the College of DuPage GFS Ensemble website, you've probably seen the graphics that I created for the SCP. Obviously at very long lead times, you can get very different depictions of supercell composite parameter given the spread in the ensemble members. And so here's an example of a 20-member postage stamp style map that looks at the supercell composite parameter for a particular given forecast. So this study is going to look at all 0Z cycles in 2016 and 2017 during the spring. We're going to chop off the first 12 hours and last 12 hours of the forecast so that we only have 12Z to 12Z periods for a total of 15 days. We're then going to match up the practically perfect outcome from those 12Z to 12Z periods with the maximum supercell composite parameter predicted over that 12Z to 12Z period. We're going to do this for, again, all spring of 16 and 17, giving us about 3,864 forecasts for both practically perfect hail and practically perfect tornado. So here's a visualization of what the forecast process looks like. Let's say we have an event. We're only interested in the slight risk aspect of the event. So for tornadoes, that would be the 5% threshold. We come up with the ensemble mean from the GFS. And so let's say that this is the spatial area of where the average supercell composite parameter value from all 21 members was greater than some value, let's say the value 2. And then of course, we could do some gridded statistics. We could say, right, in the purple is where we have a forecast hit, where we have a miss in the red, a false alarm in the blue, and everywhere else in the gray is a correct null. Now, with any forecast for extreme weather, you're going to get a lot of correct nulls, and they're going to overwhelm your skill statistics. So you really have to choose skill statistics that don't heavily weight correct nulls. So things like the critical success index, the Breyer skill score, et cetera, are much better to use than things like accuracy or probability of detection. We need to kind of remove all those correct nulls because they can really skew your forecast. We're going to grade the forecast, though, very, very similar to what we're doing with the skill statistics. I do want to show you how we visualize the forecast because this is kind of cool for those of you who are interested in extended range prediction. We do plot chiclet style charts. And so the idea here is that a forecast runs diagonally on the chart, and then the verification day sets up in a vertical column. And so in the top panel here, we're looking at the area across the United States with a CONUS value of SCP, the area across the CONUS with an SCP value of 2 or greater. This is from all the members. And then underneath, we're looking at the area of practically perfect hail greater than 5% and practically perfect, practically for tornado 5% and practically perfect hail 15%. And so you can kind of see here, you know, the areas that vertically align do correspond with bigger days of practically perfect. It's also very good at, the GEF seems to be very good at looking at quiet periods as well. But there does seem to be some, visual, again, qualitative cutoff somewhere around, say, 10 to 12 days on when the models start locking into a solution that is perhaps favorable or unfavorable for severe storms. So I'll skip that same chart for 2017, but I wanted to show you. So what we found from that study, and really the most important thing here, is the panel C that you're looking at in the lower left, the Breyer Skills Score. The Breyer Skills Score compares your skill to climatology. And so here, whenever you hit 0, your forecast is no longer more skillful than a climatological forecast. And so what we see from GEFs is that if you're forecasting tornadoes specifically directly from the model using SCP, you will have no skill beyond 9 days. For hail, you really have no skill beyond 11 or 12 days. And so if we want to look at how to be skillful in predicting severe weather beyond this benchmark, this is the new benchmark, right? It's basically 9 days for tornadoes and 11 days or 12 days for hail. We cannot use strictly numerical weather prediction to get there. We showed this from this paper, and I'll skip the rock characteristics so that we can get into the subseasonal stuff. Here's a case study of what this might look like. You're looking at the probability of the supercell composite parameter from all members being greater than or equal to 2. This is on day 15. We have about 20 to 30%, right? Maybe 40% in eastern Nebraska. Then day 14, 13, 12, 11. And now remember, we're starting to now get into day window 10. This is where we would start to see skill from the model showing up. Day 9, this is our first 60% contour. Day 8, this is critical point here because this is the first time window that the SPC can actually issue an aerial outlook for a forecast. They went with predictability too low. We did have 80% of the members that was showing an SCP value with convective precipitation of greater than 2. Day 7, still predictability too low. Day 6, there came the first aerial outlook from SPC, 15%. Day 5, day 4, day 3, we had a slight risk. Day 2, moderate risk, and day 1, we ended up with a high risk. Here's the verifying practically perfect from that particular event too. So it's just sort of a visualization of how these forecasts look. So in summary, if you're using just the GEFs, you're not going to get skill beyond day 9, 10 for tornado and 11, 12 for hail. Again, if you're solely using numerical weather prediction, that aligns pretty nicely with Ed Lorenz's chaos theory. We don't know what this skill looks like for the new GEFs, although we do have some research underway to look at that. And what I'd like to transition to here for the remainder of my presentation is the horizon beyond numerical weather prediction, which is called subseasonal severe weather forecasts. And that's this chart here looking at the orange line, this diminishment of skill, say from forecasts from 2 to 3 weeks to 3 months. We know that skill with NWP diminishes rapidly, almost exponentially as a function of time. But can we glean anything from the background environment and statistics, maybe large-scale climate variability, that can give us skill over the 0 skill of climatology at these longer lead times? And that's where a lot of my research has been focused on in the last 2 to 3 years. We've written a lot of papers published in AGU and GRL journals about these modes of variability. And the one that I really want to talk about the most here is the Madden-Julian oscillation, the MJO. The MJO is basically a number 1 through 8 in terms of its phase of where the convection or the anomalous convection is located in the Western Equatorial Pacific and Indian Ocean. So if this diagram here would basically be an MJO phase 2 moving into a phase 3. This equatorial convection with the upper level easterly winds propagates easterly in the tropics, and you'll see essentially on a phase diagram tracking the MJO is done in a counterclockwise fashion. So, in the example that I just had, that convection would have been over the Indian Ocean here in phase 2, probably moving into phase 3. And these orbits can be anywhere from 60 days to 90 days on average, depending on the speed of the propagation of the MJO signal over the maritime continent. So I want to show you how this happened in 2019. We had a significant tornado event in the central United States with 3 times the average of tornadoes that we would expect in May. And the cause of this was a deep anomalous upper level trough in the western United States. And you can see that 500 millibar height anomaly there in the west created nice southwesterly flow and strong poleward moisture anomaly into the Great Plains. Here's a very quick radar animation of that period in late May of 2019. And you can see the red boxes here are tornado watches, and the yellow boxes that pop up are severe thunderstorm watches. And every single day throughout this period, we had significant tornadoes reported and also significant hail. So this was not only a big severe weather producer, but as the convection matured and moved east towards the Mississippi River, also produced a significant amount of flooding. From our previous research, what we actually see is that there's a signal that happens in the environment, both through the MJO and another metric called AAM, or atmospheric angular momentum, where this significant increase in convection that we find over the Indian Ocean is usually happening during a very unfavorable period for severe weather across the US. And so you almost look at this diagram as if you were watching the World Series. Where do you not want to pitch this hitter? You know, they're going to hit a lot of home runs if you throw them low and inside. For tornadoes, you really like to be in this area of low atmospheric angular momentum and low atmospheric angular momentum time tendency. And that's usually when the convection is shifting, the MJO convection is shifting across the international date line into the Western Hemisphere. Here's an example of how this happened in May of 2019. This green area is where the anomalous convection is located. This was 4 weeks prior to the 2 weeks of mayhem of severe weather across the United States. And here's where the MJO is located throughout that week period. The gray circles here are the number of United States tornado reports that were happening during that period. 3 weeks, the convection moved across the maritime continent. You can see the propagation in the MJO. 2 weeks later, the MJO convection is almost out near the international date line in the Western Pacific, moving across phases 6 and 7. And then 1 week, this is 1 week prior to the event, the MJO kind of pulsing of the jet stream then retrograded and caused a huge trough in the west. And here's this 812, what we call the 812 transition, that then led to a significant outbreak of tornadoes nearly every single day throughout the period late May of 2019. Here again, synoptically, how this set up, you'll basically see a big jet extension happen across the Pacific Ocean. These are what we call jet extension and retrogression sequences. This is 1 week prior to the event, and then the big amplification and retrogression of this stationary long wave trough in the Western United States. These events don't always happen. They're what we call forecasts of opportunity. And we do have a team that's looking at the prediction of these events 2 to 3 weeks in advance called the ERTAF team. And the ERTAF team was just published in BAMS in the latest issue of BAMS. So if you want to take a look at the latest issue of BAMS, we have a paper here that describes these efforts of forecasting tornado and hail activity 2 to 3 weeks in advance. And finally, I'll sign off here in this presentation discussing that even if we have the best forecast in the world, these events are still going to happen. And so communication and understanding vulnerability are key. And so I do want to give a plug to my colleague's work at Northern Illinois, Walker Ashley, who looks a lot at societal vulnerability and the growing footprint of society, in that we can have these forecasts, you know, really great forecasts 2 to 3 weeks in advance or even the day of. But if we're not communicating those forecasts to people, we're not really taking our message across the finish line. And we're really doing disservice to the folks that probably need this information the most. So in summary, we have identified some significant modes of climate variability that do create either favorable or unfavorable conditions for tornadoes across the US. These do not always exist. They are forecasts of opportunity. And you can read more about those forecasts of opportunity in our GRL paper that looked at May of 2019. So with that, I will wrap up my presentation here, and I'm going to hand back over the controls to Sid, and I'd be happy to answer any questions that any of you have. Thanks for tuning in this rather unique online environment.
Thank you, Victor. That was a fantastic presentation. We have a few minutes left, so instead of taking back over here, we're just going to go ahead and take some questions. So if anyone has any questions for Victor, just feel free to ask.
Victor, this is Charles Ware in Atlanta. Thanks for your talk. Very interesting. What do you think the next steps are between where your researcher is now and being able to operationalize this in a weather forecast office?
That's a great question. Right now, we need a significant investment in basic research in understanding these modes of climate variability better. We don't have a great understanding right now of how many of these forecast opportunities are out there. We really need to catalog them, understand them better. It's very unlikely that they all behave the same way. I am collaborating and have collaborated in the past with both SPC and CPC, but we do see this type of research eventually develop into something like a weeks 2 and 3 temperature or precipitation outlook that would come from CPC. And so that would be something like, above normal, below average with various probabilities that would probably look very, very similar to what a CPC temperature or precipitation outlook looks like. I still think we're probably 3 or 4 years away from that, and we do need some significant investment in just kind of basic research before we get there. But I do think the new version of GEFS, taking advantage of the dynamic predictability in week 1, and then kind of marrying that with the statistical correlations that we know happen with the modes of climate variability, I think will get us a long way into, creating more skillful subseasonal forecasts. And I do want to reiterate that, there are going to be times when these are slam dunk forecasts, like this one was 4 weeks in advance that we created. But there are also going to be times when there's literally no predictability given, the modes of climate variability might not be active. So that's a great question.
Right. Thank you.
We do have one more question here in the chat. Have you found any other teleconnections or atmospheric oscillations that can be predictors of tornado outbreaks?
That's a good question, Katie. We don't likely know. It's the old Donald Rumsfeld quote, right? Of, the things that you don't know, you don't know. We know some modes of variability, like the atmospheric angular momentum, GWO, and the MJO. But it is likely that there are some other oscillations or internal variability mechanisms in there that we're not aware of. And I think things like machine learning will definitely bring those out in the future. You can imagine, artificial intelligence, give the computer a data set and let it tell you what it's important, and then go back and see if it makes physical sense. So the answer is we don't know, but we'll likely be finding those things in the future with things like AI and artificial intelligence.